So the last thing we're going to look at when it comes to phase transition is a way that we diagram and can look at the various conditions under which a substance will exist in a certain phase. And we call these diagrams phase diagrams because the phase of a material depends on both temperature and pressure. We'd like to have a diagram to look at so that if we have both conditions, we can accurately predict what phase that substance will be in. Or if we describe a transition from one temperature to another or one pressure to another, what kind of transition are we going to describe? And the typical phase diagram for most substances looks like this, where at low temperatures, and high pressure, those things exist as solids. And you can kind of see that line that divides solids from the rest of the phases. And then at high temperatures and low pressure, substances typically exist as a gas. You can see that boundary there. And then you have liquids here. You can see at somewhat high pressure, somewhat high temperature. Now, a couple of points to that I want to highlight on this is the intersection of all three of these lines, something known as the triple point. The triple point is where all three phases coexist in equilibrium. So it's kind of this unique point. It's just one single combination of temperature and pressure where that substance will exist in all three states of matter. And then this point here on this gas curve is known as the critical point. And basically, above that, so as we're going up here, we create what's called a supercritical fluid, which is a substance that has properties of gases and liquids. Now, when we transition from one phase to another, we're describing some sort of, as I said, transition. And so, like, for example, if we go from a gas, if we start over here and we just lower the temperature, so we keep pressure constant, we're going to condense that. Or we could say the same thing if we start here in the gas and we move this way, keep temperature constant, but increase the pressure. That's also going to cause condensation. So what you should basically be able to do is describe these transitions. Like if we're crossing the boundary of a line, what does that describe? Or if I give you a set of temperature and pressure conditions, you should be able to read the graph and tell me what phase of matter that substance will be in. Now, for a little bit more specific of an example, here is the phase diagram for water. Now, one of the things I want to point out is notice it looks a little different than the sample one I did on the left here, which is true for most substances. And what's different is the direction of this line, the slope of this line. This is kind of unique to water. There's very few substances that have this kind of phase diagram. And what this kind of represents is that as pressure increases, water tends to be a liquid. Even at low temperatures. And this is relates to a property of water that you've probably observed, but water is rare in that its solid form occupies more volume than its liquid form. Basically, water expands when it freezes. And we might have seen this if you put, you fill up a glass bottle with water and like to the brim and cap it, and then put it in your freezer. When give it a few hours till everything freezes, that since the water expands, it's going to shatter outside and cause the glass to break apart. Um, I don't, recommend doing that unless you like, if you want to try it out, put it in like a plastic bag, so that you don't get glass all over your freezer. But it's one of these kind of rare qualities that is unique, not to water only, but there's very few substances that have this kind of same looking phase diagram as water. So as I said, you should be able to interpret these phase diagrams. So for example, if I were to give you this phase diagram of water and ask you um, what state of matter will water exist in at 100 degrees Celsius and um, zero point 0.5 kilopascals? Well, 100 degrees Celsius is here, and zero point 0.5 kilopascals is probably about here. And so it's going to exist as a gas.